Today's the day where we're actually going to start waves. We've done a lot of things with sine curves and pendulums and springs. Today's where we get into waves proper. Just a quick reminder of the pendulum, how it traced out our sine curves with its repetitive motion, period and frequency. Formula to calculate the period. Get the reciprocal, you can put it into the sine curve equation and track the pendulum. Same thing with the object on the spring. We have the same exact formula, but a different way of calculating period. We've seen all this. Today we'd like to talk about waves. And probably you're most familiar with waves when we look at water. So here we have a nice calm pond. We're going to drop a little rock in, and you're going to see the ripples move outward in all directions. Those ripples are what we know as a wave. A wave is a disturbance that propagates through space and time. It's the propagation of a disturbance through space and time. The disturbance happens here, and it moves through space and time. This is what we know as a wave. Again, waves start with a disturbance. So you'll notice I've got a rope from the front of the room to the back of the room. We're going to whack the rope in the back, and you'll see that disturbance traveling to the front, boom, and then traveling back to the back of the room. Propagation of a disturbance through space and time. Okay, so one more time. We see it travel toward the front of the room, boom, and we see it go back again. Notice, the wave is a transfer of energy and not a transfer of matter. No actual matter traveled from the back of the room to the front. It was simply a pulse of energy. We see waves when we talk about guitar strings, and again, these waves are started by a disturbance. So as you pluck the different strings, that disturbance is going to travel up and down throughout the string. In a few days, we will learn how to calculate what frequency of sound is going to come out of our strings under different circumstances. Again, with the speaker, the sound comes from a disturbance. Okay? The disturbance propagates through space and time. Drum, same thing. Starts with a disturbance, travels outward through space and time. Recently, I was in Rancocas Woods, and I had this tree creating a weird noise. And again, you could see it was the wind making the leaves rattle. The disturbance was the vibrating leaves. With light, it's a disturbance of electric and magnetic fields, and I know we didn't cover them in much detail, but I do want you to know that light is a disturbance of an electric or a magnetic field that again propagates outward away from the source of the disturbance. When we talk waves with the ocean, we're talking about when they are way out there beyond the breakers. You'll notice again how the people didn't move, because it's a pulse of energy that lifts them and drops them and doesn't actually carry them in toward shore. When they're moving in toward shore, it's technically not a wave anymore. It's a breaker. At that point, it does not follow our rules. Okay, our rules are when it's a wave, where it's a disturbance, but not actually a transfer of matter. We can see this really good with the exercise ropes.
For 30 seconds. Let's go, Daniel. Oh, great job. Lean back just a little bit. Good, good, good. Great.
Okay, so you can see she starts with the disturbance and it travels through the rope. Disturbance traveling through space and time. And again, if we pause this, I hope you guys can see the sine curve that occurs when we have a wave. Note, if you're looking at your sine curve, it's not stationary. it propagates, it moves. So it's like a moving sine curve. You can think of the wave like a moving sine curve. These little balls represent particles on the rope. Notice they don't go anywhere. They go up and down, but they don't travel. The only thing traveling is the disturbance, the energy pulse, okay? Transfer of energy, not a transfer of matter. Two ways of looking at a wave because it's pretty complicated. We have a moving sine curve, so we got to stop it somehow. One way we could stop it is to take a picture of it, like I did a few moments ago. And if you take a picture, you'll notice your x-axis is no longer time. It is horizontal position. And now, this does not represent time, it represents a wavelength, the length of one wave. You have to look at the x-axis, and if it's a position measurement on the x-axis, then the distance from one wave to the other is called the wavelength. If, on the other hand, you are just looking at one spot on the wave and you're watching it go up and down, kind of like an object on a spring or a pendulum, it's going to trace out a sine curve. Now when you look, the x-axis is time, so this is not wavelength, this is now period measured in seconds. So again, wavelength measured in meters, period measured in seconds. Okay, I'm going to ask you to try a couple problems. I'd like you to find the wavelength amplitude of this wave. So again, horizontal position is on the x. So look at where you start, look at where you end, make sure you're doing one wave. If you want, you can measure the distance for two waves, it'll be more accurate. Just remember the divide by 2. For amplitude, remember that is the distance from the average point to your most extreme point. So see if you can find the amplitude and wavelength from this type of graph. Okay, with this graph, you're going to be looking for period, frequency, and amplitude. This time we're graphing it versus time. So again, start here, do lots of cycles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cycles in about 7.9 seconds. You should be able to find the frequency and the period. To get the amplitude again, find your average and see how much you deviate from the average. All right, so best of luck. Hopefully you are able to work with your sine curves when time is on the x-axis or when position is on the x-axis. Hopefully you understand these are the same wave. It's just that one of them is a picture and one of them is tracking a single object. So if we watch this, if we freeze it in time, we can see wavelength. And if we just watch one object go up and down, we can get period and frequency. I want you to remember that waves are started by a disturbance. They propagate through space and time, and the material doesn't go anywhere. It just oscillates up and down. Okay? The only thing that travels from right to left is the energy pulse. With light waves, it's an oscillation of the electric and magnetic field. And for sound waves, again, they're always started by some sort of disturbance.